And there are two experimental ways to determine a rate law. The first one that we're going to talk about is the method of initial rates. And then the second one we're going to talk about, I actually already gave you a very tiny glimpse into when we did the graphing lab. And that is we're going to talk about integrated rate laws. So first of all, let's talk about the rate law. The rate law describes the relationship between the rate of the reaction and the concentration of the reactants. The rate law is going to look at a much broader picture than does the instantaneous rates we talked about yesterday. So here we have a very generic reaction where you have the coefficient A times the concentration of A plus the coefficient of B times the concentration of B goes to yield the coefficient of C times C plus D times D. The first thing you need to know about a rate law is a rate law has a generic equation. First of all, in the rate law is the rate. That is equal to a lowercase k, which represents the rate constant. That rate constant is multiplied by the concentration of the first reactant raised to an order times the concentration of the second reactant raised to an order. So here, again, the K, the lowercase k, represents the rate constant. Once again, brackets, anytime you see brackets, that is representing concentration. So we're typically going to be talking molarity. M and N in this rate law represents the order with respect to that particular reactant. To figure out the overall order with respect to the reaction, you would add M and N together. Notice in the rate law, the only thing represented are the reactants. So again, it's the rate is equal to the rate constant times the first reactant raised to that reactant's order times the second reactant raised to that reactant's order. It only includes the reactants. Rate laws will never include the products. You can always start any reaction by writing the generic rate law. What we need to do is we need to specifically be able to figure out the order of each of those reactants. And that is where the method of initial rates comes in, or the integrated rate laws come in. Those are the two methods that allow us to determine those superscripts of M and N, respectively. Now, the most common orders. You can have something that is zero order. If you have the concentration of A to the zero order, again, that is describing the order with respect to that reactant. What is anything raised to the power of 0? 1. So therefore, the rate of the reaction is independent of the concentration of that reactant. The second most, or another common order, is first order. Now, a lot of times we don't actually illustrate the order if it is first order. We just simply write the reactant in our rate law. Now, let's look at how the order impacts the rate of this reaction. Let's say my concentration is 1 raised to the power of 1. Well, anything raised to the power of 1 is itself. Let's say the concentration is 2 raised to the power of 1. Well, anything raised to the power of 1 is itself. So in other words, if I double the concentration, I double the rate of the reaction. Meaning that the rate is directly proportional to the concentration of the reactant. The third common order is second order. Which would be represented as A squared. Now, using the same analogy that I used previously, if I have 1 squared, well, 1 squared is 1. But if my concentration is 2 squared, now it is 4. Meaning that if I double the concentration, I quadruple the rate of the reaction. So the rate is proportional to the square of the reactant concentrations. Now, what does I've said it's called the order. What does the order mean? What it means, folks, is how many of those reactant molecules take part in the collision. What it means is how many of those reactant molecules take part in the collision. In this particular case, none of A takes part in the collision. It does not matter that A even exists. In this one, it means that one A molecule takes part in every collision to get the reaction to occur. And in this one, it means 2 A molecules take part in every collision. Now, that's going to be an important concept because I have rate equals K times A to the 1 times B squared. What this means is each collision requires 1A and 2 B's to collide with the correct energy to cause the reaction and with the correct orientation. Meaning we have to have 3 molecules collide perfectly. While there are some reactions that will require 4 molecules or more to collide, those reactions are very, very few and far in between. Because getting 3 molecules in this vat to come together simultaneously with the correct orientation and the correct energy is very difficult. So if you're trying to get 4 or more, it's just not really feasible. And then, so this reaction is, again, first order in A, second order in B, which means it's third order overall. It's third order overall because 3 molecules must collide simultaneously with the correct energy in the correct orientation for the reaction to occur. So when we're describing the order, we're describing the number of that particular particle that must collide for the reaction to occur. Now, unlike coefficients cannot be, coefficients must be positive whole numbers. Unlike coefficients of a balanced chemical equation, orders do not have to be whole numbers. They can be fractions. They can be negative. But no matter what they are, this is your general rate law. Now, again, as I said, those orders must be determined experimentally. And there are 2 ways that we can determine the orders experimentally. One is to use what is known as the method of initial rates. The initial rate is going to be the rate for a short period of time at the beginning of the reaction, and it is determined by running the reaction several times with different initial concentrations. Again, the initial rate, the method of initial rates, when we're talking the initial rate, we're talking the rate for a short period of time at the beginning of the reaction. And it's measured by running the reaction several times with differing concentrations. Next week in lab, you will be using this method of initial rates to determine the bleach concentration for the reaction we are studying. The second method that we will tend to use to determine the orders is going to be the integrated rate laws. Next week in lab, you are going to use the integrated rate law to determine the dye order for the reaction we are studying. DYE order. So in other words, like blue dye and red dye and that type of dye. So let's look at an example. We're going to look at a couple of examples. When we do this method of initial rates, the first thing you're going to see me do is write the general rate law for the reaction using generic orders of M and N. The second thing we're going to do with the method of initial rates is we're going to set up a ratio of the general rate law for the first reaction versus the general rate law for the second reaction. We're then going to solve. So let's look at the first example here. Determine the rate law for A goes to form products in a reaction where the initial rate is measured at several different initial concentrations, and you obtain the following results. We're going to call this experiment 1, experiment 2, and experiment 3. The generic rate law for this is going to be rate is equal to the rate constant times the reactant raised to an order. Now, I said we're going to start by writing the generic rate law. We're then going to make a ratio. What I mean by that is we're going to take rate of reaction, and it doesn't matter which one you choose, you'll get the right answer, but I'm going to choose rate of reaction 2 is equal to the rate constant times A of reaction 2 raised to its coefficient, its order. And we're going to divide that by the rate law for reaction 1, which is going to be rate is equal to K times A1 raised to the order. Now, in this particular case, the rate constant is going to cancel out because as the term describes, it's a constant. Now I'm going to plug in the information. So the initial rate of 0.030 for reaction 2 divided by 0.015 for reaction 1 is equal to the concentration of reaction 2 which is 0.20, divided by the concentration of reactant 1, which is 0.10, raised to the order. Now, this comes out to be 2 is equal to 2 raised to some power. Now, you should know what that power is. But let's say it is something you cannot easily predict. How do you get it? Well, the way you go about getting this is you take the log base 10 of both sides. So that would be the log of 2 is equal to, and when you take the log base 10 of the right-hand side, that order comes out and it's m log 2. But dividing both sides through by log 2, you can see that m is equal to 1. So my rate law is that the rate is equal to K times A. And again, we don't tend to represent the superscript of 1. It is just understood. That one was fairly straightforward. The next one should be fairly straightforward relative, but it's going to take a bit more work. Questions about this problem? Okay. Consider the reaction between nitrogen dioxide and carbon monoxide to form nitrogen monoxide and carbon dioxide. I give you the initial rates on the next page. We're asked to determine the rate law, and we're asked to determine the rate constant. First of all, we're again going back to the way I described things. The first thing we're going to do is write a generic reaction rate law. So our rate is going to be equal to our rate constant times the nitrogen dioxide concentration times the carbon monoxide concentration. Whoops, I forgot to raise those to a power. Again, I'm going to be using this generic rate law, and I'm going to be setting up a ratio between experiments. Now, in this particular case, we have to add another step. To determine the order of nitrogen dioxide, hold the carbon monoxide constant. And to determine the carbon monoxide order. Hold the nitrogen dioxide concentration constant. So what does that mean? Okay, we have experiment numbers here. Again, if I want the nitrogen dioxide concentration, I have to hold the carbon monoxide constant. The carbon monoxide that is constant in experiment 1 and 2. To determine the order of carbon monoxide, I've got to hold the nitrogen dioxide concentration constant. The nitrogen dioxide concentration is constant in experiment 2 and 3. So when we're setting up our ratios, we are going to do so using those particular experiments for that substance. Okay, so for our nitrogen dioxide, that means it's going to be rate 2 is equal to the rate constant times the nitrogen dioxide concentration of experiment 2 raised to the order times the carbon monoxide concentration of experiment 2 raised to its order, divided by rate of experiment 1 is equal to the K times the nitrogen dioxide concentration for experiment 1 raised to its order times the carbon monoxide concentration for experiment 1 raised to its order. Now, plugging in this information, you get 0.0082 divided by 0.0021. That's equal to the rate constant for experiment 2 times the concentration of experiment 2, which is 0.2 raised to its power, times the carbon dioxide concentration of 0.1 raised to its power, all divided by K, times the experiment 1 concentration of nitrogen dioxide, which is 0.1 raised to its power, times the carbon monoxide concentration of 0.1 raised to its power. All I did was take these generic equations and plug in the values. Now you can see why we had to hold the carbon monoxide concentration constant. Because by holding the carbon monoxide concentration constant, the carbon monoxide concentration and the rate constant disappear. Therefore, this becomes 0.0082 divided by 0.0021 is equal to 0.2 divided by 0.1 raised to the power of m. When dealing with this, we do tend to, if it's really close to a whole number, we round to the whole number. So this left-hand side is going to round to 4. That is equal to 2 raised to the power of m. Again, you should be able to recognize what that order is. However, this one is straightforward. Sometimes they're not. So I'm going to go ahead and illustrate the math. We would take the natural log of 4 is equal to m times the natural log of 2. Therefore, the log of 4 divided by the log of 2 is equal to m. So therefore, 2 is equal to m. You don't have to go through those last few steps. And in fact, you can even shorten from here to here, as long as you understand what you're doing and why you're doing it. I wrote out everything just so that I could illustrate that we held the carbon monoxide concentration constant for a reason, so that these two would cancel out, the K would cancel, and that would allow us to easily determine the order of the nitrogen dioxide. Take a moment and figure out the order of carbon monoxide. When you did the math, you should have gotten a order for carbon monoxide of 0. Therefore, the rate law for this reaction is rate is equal to K times the nitrogen dioxide concentration squared times the carbon monoxide concentration to the 0, but anything to the 0 is 1. So typically, you simply write it as rate is equal to K times NO2 squared. I will say on my calculator, if I forgot a parentheses on my logarithm, it came out the wrong answer. So you had to make sure that you had the log of 1 in parentheses divided by the log of 2 in parentheses. So that means that it is second order in nitrogen dioxide. It is 0th order in carbon monoxide. And it is second order overall. Now, I'm looking for the exact problem so that I don't have to go back and forth on my data. You wonder what I'm doing? Okay. Now, the other thing it asks for is for the rate constant. With using, for the method of initial rates, you can take any one reaction and plug in the data to the rate law to solve for the rate constant. So for example, we determined that the reaction was rate is equal to K times NO2 squared. So to figure out K, I'm just going to pick the first reaction. It was, the rate was 0.0021 is equal to the rate constant times 0.1 squared. So completing this calculation, you get a rate constant of 0.21. And that rate constant is going to have the units of per molar second. Now you may ask how I came up with those units. Well,
let's just look at the units of our information. The left-hand side is molar per second because all initial rates are in molar per second. That is equal to the rate constant. And then we have the concentration squared, so molar squared. So we have molar per second divided by molar squared is equal to K. So our K comes out to be equal to molar to the -1, second to the -1, or in other words, those units are in the denominator. Questions? Yes, I follow my units a lot to figure things out. Any questions about method of initial rates? Okay, before I move on to integrated rate laws, I did want to mention that as of 4 something this morning, the next 2 homeworks, which I told you would have 2 this week, were posted. The first homework is over concentration units. There's a few concentration units to calculate and a couple of them that you have to do concentration unit conversion. The second homework starts with the information we discussed yesterday and goes through the method of initial rates. I did want to make one note, and I made it yesterday in the lecture as I was going through things. When we're dealing with Van Hoff factor, what we did in the laboratory is we used the expected Van Hoff factor. But in a couple of the problems that you have to work with the Van Hoff factor, they gave you the real value. So make sure you're using the real Van Hoff factor, which I mentioned in lab may be the case. But I wanted to let you know that it was definitively the case. Questions for me? And even though we went through a lot of information, I did try to keep it relatively short, giving you at least one of every example. I didn't try to give you a ton of every example, because otherwise it would have been extremely long. So, any questions for me? Okay, then what we're going to do now is we're going to get into integrated rate laws. First of all, when you're in an experimental setting, what you do is you collect a series of data versus time. You then graph that series of data versus time, the natural log of that series of data versus time, and 1 over that series of data versus time in order to determine the order with respect to it, the substance that you are analyzing experimentally. So, for example, on Monday, you'll be taking bleach and adding it to blue dye. When you first perform that, you're going to get the initial rate of, you're going to get the initial concentration based off of absorbance using a UV vis spectrometer. You are then going to measure what happens in that cuvette over, I think it's 20 minutes. Now, as would be expected, the dye is going to disappear. So the absorbance is going to continually go down. Relative, because the dye is disappearing, and that's what we can actually tell using absorbance. But anyhow, you're going to take and you're going to get the concentration, essentially, of the dye versus time of 20 minutes. And you're just going to take this huge series of data. You're then going to graph that data. And you're going to graph the concentration versus time. You're going to graph the natural log of concentration versus time. And you're going to graph 1 over the concentration versus time. Whichever one gives you the best straight line tells you the order. And that uses integrated rate laws. So again, an integrated rate law is determined by analyzing the relationship between the concentration of the reactants versus time. The order is determined by graphing. Okay. So, if it's 0 order, that means the rate is equal to K times our reactant raised to the 0 power. Because anything raised to the 0 power is 1, it means that the rate is equal to the rate constant. It means that the rate is completely independent of that concentration. When you are graphing, you will know it's 0 order if time on the x-axis versus the concentration on the y-axis gives you the best straight line. Meaning you will know that it is 0 order if time versus concentration gives you the best R squared for a straight line. Now,
The integrated rate law can be determined based off of this straight line. The y-axis, as illustrated in this graph, is the concentration at a specific time. That is equal to the slope of the line times the x-axis, which is time, plus the y-intercept. And in this case, the y-intercept is going to be equal to the original concentration of your solution. When you are doing a zero order graph, the slope of the line will always be negative. Because it is expected that the concentration of the reactant is going to decrease as you increase in time. Therefore, the slope of the line is equal to a negative K. So this means that we can use the slope of our line to figure out the rate constant by setting up this equation and solving. Now, we can also determine the half-life. What a half-life represents is it represents the time it takes for half of the substance to disappear. Now, in an integrated rate law, or from this integrated rate law, what we find out is that the half-life, the time it takes for half of the substance to disappear, is equal to the initial concentration divided by 2 times the rate constant. If it's first order, that means our rate law, as already explained, would be equal to the rate constant times the concentration of the reactant raised to the power of 1. Now again, we don't tend to illustrate ones, just like we didn't illustrate ones when we developed the chemical formula for a compound. We don't tend to illustrate ones, they are assumed. In this particular case, since that's a constant, folks, that means that the rate is directly related to the concentration. Now, from a graphing perspective, if when you are developing your 3 graphs, it's always developing 3 graphs. If when you are developing your 3 graphs, the natural log of concentration versus time gives you the best R squared, that means it is first order. The integrated rate law, therefore, y equals mx plus b. So y is the natural log of concentration at any given time, is equal to m. The slope is equal to a negative rate constant times x, which is your time, plus the natural log of the initial concentration, which is your y-intercept. When you graph this, all of these values will wind up negative. And you will have a slope that is a negative slope. That's because we expect the natural log of the concentration versus time to go down. Now, when you rearrange this to solve for the half-life, that means that the half-life is going to equal 0.693 over K, because it's the natural log of 2, which I think is 0.693 over K. Finally, second order. You have your equation that shows that it is second order with respect to that particular substance. You will notice that since K is a constant, that means that the rate is directly proportional to the square of the concentration. Now, when you develop your three graphs, if the best R squared is obtained when you graph 1 over the concentration versus time, that means that it is second order. Of all of your graphs, this will be the only one with a positive slope. So the slope is directly related to K. You don't have to do any manipulation. It's there. One thing I will note, something you may want to put a star beside, because I see it every time I give a test. Rate constants cannot be negative. Rate constants cannot be negative. The integrated rate law, y equals mx plus b. So y is 1 over the concentration at any given time. The slope is equal to the rate constant. Your x-axis is time, and your y-intercept is 1 over the initial concentration. Your y-intercept. I think I said that. And as far as your half-life, if you rearrange all of this and solve for the half-life, you'll find that the half-life is 1 over K times the original concentration. Right now, all I'm doing is giving you the details. Again, I will work at least one problem. We'll actually work a couple of problems. I'm not going to have time today because the first one takes graphing. But I do want to show you this table, which you can find if you have the textbook on page 629. It is table 14.2. If you don't have a textbook, taking a picture of it and putting it in your notes is a good thing, because this summarizes
what I've just been describing on that slide by slide basis. For some reason, the brackets didn't show up. So you will have to go in and, I mean, if you look at the table in the textbook, it's perfectly fine, but if you look at this, you do have to realize it's got brackets around every A. For some reason, it did not show up. Neither did the negative, so I'm not entirely certain. One thing I do want to point out though is this column. Your rate, one thing that I haven't mentioned that is valid is your rate constant. The rate constant for zero order is molar per second, is the units for the rate constant. For first order, the unit is simply per second. And for second order, the rate constant is per molar second. Otherwise, I am up to graphing and illustrating it, so I'm going to cut class here. I will graph and illustrate. What are you going over today in SI, Lillian? Integrated rate laws or mainly method of initial rate? Today, Elian will be going over method of initial rate. And then any questions you have, I'm sure, from previous. So don't forget there's SI from 6 to 7 tonight in 105. Okay. I'm glad you brought something to sign with because I don't have it. I hope so. I mean, it doesn't bother me, but
I'll mostly be missing Fridays, which won't affect this time.
Right.
I'm missing on a Thursday.
okay. So the biggest,
But I'll let you know before I miss the Thursday.
right? The biggest one is going to be paying attention to test day.
Yes.
And if you have to miss a test day, which I would like to know as early as possible,
Totally. I'll try.
we can usually plan. And there's only one other Thursday test, and that is the Thursday right before spring break.
Okay.
If you're going to miss that, we can try to make it on the Wednesday before spring break.
Yes. Okay. Yeah. I'll let you know like a week.
The rest of them are Tuesday. The other two are
Okay.
Tuesdays.
That's okay. That works perfectly.
So yeah, we do have one on Thursday, and that is the Thursday before spring.
Okay. I can check what date that is and if I'm missing it.
I don't know right off the top of my head.
me
I
neither.
think it's, yeah, I think it's 320.
Okay.
So you'll need to take it on 319.
Okay. I'll let you
And
know.
I'll
the
have
week
it
before.
prepped by then because I'm not going to be here that Thursday either. I'll have somebody proctoring for me.
Okay. Perfect.
So I can give it to you on Wednesday. the
Yeah.
day before.
That sounds great. Thank you so much.
No worries.
Hey, did the attendance sheet go around?
Yes, it did. It went somewhere. I don't know where. I don't.
Oh, okay, I just pull it out of my bag, no big deal.
I didn't read it.
Okay, cool, thank you, I appreciate it. I appreciate it.
How are we doing?
Good, this wasn't bad at all.
Hi.
I think I'll need to go over it a little more because my brain's like, wait. So I think also
There's a lot
yeah,
of little details that can be.
it's a lot of memorizing. Yeah. That's what I realized. I'm probably gonna go to Elias and I'd be like, all right. Help a little. It's like I don't think I'm too lost. Also didn't help that I was a little late this morning. I was really kind of frustrated about that, but I think once I kind of got into it.